Hello students, welcome back. In this lecture, we're going to talk about sampling methods, and the central limit theorem. So there are 5 learning objectives for this chapter. The first one is to explain why populations are sampled and describe 4 methods to sample a population. The second one is to define sampling error. Third is to explain sampling distribution of the sample mean. Fourth, recite the central limit theorem and define the mean and standard error of the sampling distribution of the sample mean. And lastly, to apply the central limit theorem to calculate probabilities. So let's start with reasons for sampling a population. Well, basically, there are many practical reasons why we prefer to select portions or samples of a population to observe and measure when studying characteristics of a population, such as mean or variance. Well, first is to contact the whole populations will be time-consuming, and the cost of studying all the items in a population may be prohibitive. The physical impossibility of checking all items in the population, and the destructive nature of some tests. And so these are not, so basically there are 4 probability sampling methods that we can use, but note that these are not the only methods of sampling available to a researcher. If you become involved in a major research project, consult the books devoted to sample theory and sample design to provide you with a better and a more comprehensive description on the probability sampling methods. But in general, here are the probability sampling methods that will be discussed in this lecture. So the first one is the simple random sample. So basically all members of the population have the same chance of being selected for the sample. And we have a systematic sample. So it's a random starting point is selected. And then every kth item, therefore, thereafter is selected for the sample. We also have a stratified sample. So basically the population is divided into several groups called strata. And then a random sample is selected for each stratum. The fourth one is called the clustered sampling. So the population is divided into primary units. Then samples are drawn from the primary units. We'll talk about examples of clustered sampling when we get to the discussion. Now, first off, let's start with a simple random sampling. So basically, simple random sampling is the most widely used method of sampling. It's basically a sample selected so that each item or person in the population has the same chance of being selected. So in an unbiased sample, all members of the population have the same chance of being selected for the sample. If the population is quite small, one could place all items of interest, say names, in a box and select the sample. So basically you draw the names of the individuals. However, for large samples like the one in the example of this chapter, it's going to be time consuming if we put it in a box and then select it for sample. What we can do is we can use statistical software to do the random sample selection. For example, you can do as basic as using Stata, Excel, or you can do Stata, or you can use R for the simple random sampling. So basically there were 750 Major League Baseball players at the end of the 2016 season. A committee of 10 players is to be formed to study the issue of concussions. To make sure every player has an equal chance of being selected, we're going to write each name on a piece of paper and place the names in a box and mix them up, then draw 10 names. Okay, we can also use a table of random numbers. Now suppose that the population of interest is 750 Major League Baseball players, and on the active rosters of the 30 teams at the end of the 2016 season. And then a committee of 10 players is to be formed to study the issue of concussions. And to make sure every player has an equal chance of being selected, we can use a table of random numbers. So basically we're going to prepare a list of all players and number them 1 through 750, and then randomly pick a starting place in the random number table and then select 10 3-digit numbers between 1 and 750. So this is something that we can do we will provide you an example using Microsoft Excel, which is going to be quite straightforward in this particular place. Okay. So the next step is called the systematic random sampling. So basically, if you do not have a list of the entire population to begin with, you can use the systematic random sample. Now, in a systematic random sample, a random starting point is selected, and then every kth member of the population is going to be selected. Now, we have to be careful that if the population is sum ordered already, for example, like invoices arranged in increasing dollar amounts, the systematic procedure should not be used. Okay, so let's take an example of, so there are two examples. The first one is Toots Grocery Store wants to study the length of time consumers spend in their store. And the second, randomly select 3 days of the week, the times and starting point of the study, then systematically select the customers and measure the time each spends in the store. And the third method is called the stratified random sampling. So basically, we can divide the population into groups based on some characteristics, and let's talk about an example of the characteristics of interest, and then we're going to use stratified random sampling. Okay, so an example here is a study of 50 of the 352 largest US firms and spending. So we're going to begin by identifying the strata, then use random sampling within each group based on relative frequencies to collect the sample. So this example of stratified random sampling groups the firm by probability, measured by the percent return on equity, and the advantage of stratified random sampling is that this method may accurately reflect the population characteristics, since at least one firm will be selected from each strata, even those with low numbers, which might not happen when using random sampling or systematic random sampling. And the last sampling method that we're going to discuss in this particular lecture is called the cluster sampling. So cluster sampling is a common type of sampling used to reduce the cost of sampling over large geographic areas. So a population is divided into clusters using naturally occurring geographic or other boundaries. Then clusters are randomly selected, and a sample is collected by randomly selecting each cluster. And so basically, we can have clusters as such as village, desa or dusun, for example. We can also have kecamatan or sub-district as a cluster. And then within each cluster, we're going to randomly select individuals, or we can randomly select households. Now, in this particular example, suppose that we wish to sample residents of the 12 counties in the greater Chicago area about the government policy. We're going to randomly select 3 counties and then select a random sample of the residents in each of the 3 counties. Okay. Now, given that we discuss sampling, it's also quite important for us to discuss sampling error. So basically, sampling error is basically the difference between a sample statistics and its corresponding population parameter. The idea is that it's very unlikely that the mean of sample will be exactly equal to the mean of the population. Okay, so let's provide you guys with an example. So the Foxtrot Inn's numbers of rooms rented in June, the mean number of rooms rented or mu is 3.13. So it's going to be the population parameter, or the population mean. Now suppose that we take 3 random samples of size 5, and the sample means of the random sample size 5 is 3.80, and then the next one is 3.40, and the other one is quite low, which is 1.80. And so basically the sampling error is going to be the difference between the sample mean x bar and the population mu. So suppose that the sample mean is 380, and so the sampling error is going to be 0.67. If the sample mean is 340, then the sampling error is going to be 0.27. And if the sampling sample mean is 1.80, then the sampling error is going to be negative 1.33. Okay, so notice that the sampling error may be positive, it could also be negative. Okay. So how can we determine how accurate the sample mean is? In this particular case, we need to look at what's called the sampling distribution of the sample mean. So basically, a probability distribution of all possible sample means of a given sample size. So for a given sample size, the mean of all possible sample means selected from a population is equal to the population mean. There is less variation in the distribution of the sample mean than in the population distribution. And the sampling distribution of the sample mean tends to become bell-shaped, particularly particularly if we have very large observations. Okay. So let's talk about the sampling distribution examples. So Tartus Industries have 7 production employees, the population. And the target hourly earnings of each employee is given in the table. What is the population mean? What is the sampling distribution of the sample mean for sample size of 2? What is the mean of the sampling distribution, and what observations can be made about the population and about the sampling distribution? Okay, so this is an example of using a sample population of just 7 to highlight the relationship between the population and the various sample means. Okay, so first let's calculate the population mean. So the population mean basically is just the sum of all the hourly earnings divided by 7, which is the total observations in the population. And so the population mean is $15.43. And the next nice is, what is the sampling distribution of the sample mean for sample size of 2? So basically, since we have 7 sample, and so basically what we can do is we can randomly choose 2. Okay, so given so in this particular case, we can have 21 possible samples from the population of 7. So you can have Joe and Sam, Joe and Sue, Joe and Bob, and so on until Art and Ted. And so, for example, if we randomly select Joe and Sam, then the sample mean for Joe and Sam is 14. However, let's look at sample number 7, Sam and Sue. Sam and Sue have has an average of $15. And let's take another example is sample 20, which is John and Ted. So basically for John and Ted, the sample mean is 16. So basically, even though the population average is $15.43, what we can see here is that the sample mean is actually very different from one sample to the other. However, you can notice that there are several observations with similar sample mean. So 14, 15, 16, and 17. And so given that, we can actually count the number of means with number of means for $14 and then $17. And so basically we have the total number of means, 21 total number of means, and then we can have the probability for each of the sample mean. So for example, for the sample mean of $14, the probability is 3/21, which is 0.1429. And for a sample mean of 16, the probability is 0.2857. And so basically we can count the mean of the sample mean. Basically it's the sum of all sample means, which is $324 divided by 21, and we get 15.43. And so you can see here is that the population mean is equal to the average of the sample mean. So again, the population is not going to be equal to the sample mean, but the population mean is going to be equal to the average of the sample mean. This particular case is 15.43. And in this particular case, we can say that the sample mean is a non-biased estimate of the population mean. Okay, so what observations can be made about the population and of the sampling distribution? So the mean of the population is exactly equal to the mean of the sample means. So although the sample mean ranges from $14 to $70, while the population values range from 14 to 18, the shape of the sampling distribution of the sample mean and the shape of the frequency distribution of the population values are quite different. You know, as we can see in the chart 8.2, the distribution of the sample mean tends to be more of a bell shape and approximate the normal distribution. So it's a good time to revisit the central limit theorem once again. This is something that we've seen earlier, but it's always good to revisit central limit theorem since we're talking about sampling distribution. So the central limit theorem is one of the most useful conclusions in statistics and is true for all population distributions. So the central limit theorem allows us to use the normal probability distribution to create confidence interval for the population mean, which is going to be discussed in chapter 9, and perform tests of hypothesis in chapter 10. So basically, if the population follows a normal probability distribution, then the sampling distribution will also be normal. However, this is when it gets interesting. If the population distribution is symmetrical, you will see the normal shape of the distribution of the sample mean emerge with samples as small as 10. If the distribution is skewed or has thick tails, then it may require samples of 30 or more to observe normality feature. So as you have more sample in your data, then the sampling distribution is going to be very close to the normal distribution. Okay, so let's take a different look at a different population distribution. So in the left one, you have a different distribution. So basically, it's a kind of like a like a hollow distribution, and then in the second one, you have kind of like a triangular distribution, and the third one is you have what's called the uniform distribution, and on the right you have kind of like a downward sloping distribution. Okay, so basically following each of this population downward, let's start with the sampling distribution if you have a random sample of size 2. Okay, so you can see that the shape of the sampling distribution when the sample size is 2 is quite different with the population distribution. Another thing which is interesting to see is actually the shape of the distribution when the sample size is 6. You can see that for population for column 1, 2, and 3, the distribution already looks like a normal distribution. And if you have a sample size of 30, then what you can see is a normal distribution. So the mean of the distribution of sample means will be exactly equal to the population mean if we select all possible samples of the same size from the population. The standard deviation of the sampling distribution of the sample mean is also called the standard error of the mean. So basically, there will be less dispersion in the sampling distribution of the sample mean, sigma divided by square root of n, than in population. Another thing that you can observe is that the sample mean, the standard error of the mean, is a function of the sample size n. So basically, when the sample size is increased, the standard error of the mean decreases. In other words, if you have more sample, then the standard error decreases, or the precision of the estimate is going to be higher. This is an important feature of the central limit theory conclusions. Okay, so if the population follows a normal distribution, the sampling distribution of the sample mean will also follow the normal distribution for samples of any size. If the population is not normally distributed, the sampling distribution of the sample mean will approach a normal distribution when the sample size is at least 30. That's why you hear in a lot of instances that it's always good to have at least 30 observations. For the following reason, if that the sample size is at least 30, then the sample mean will approach the sampling distribution of the sample mean will approach a normal distribution. Now assume that the standard deviation is known. To determine the probability that a sample mean falls in a particular region, we can always use the standardized normal formula, or the Z formula. Okay, so let's use the sampling distribution example and discuss this particular case. So the Quality Assurance Department for Cola Inc. maintained records regarding the amount of cola in its jumbo bottle. So the actual amount of cola in each bottle varies a small amount from the one bottle to another. Records indicate that the amounts of cola follow the normal distribution. The mean amount of cola in the bottle is 31.2 ounces and the standard deviation is 0.4 ounces. At 8 a.m. today, the quality technician randomly selected 16 bottles from the filling line. The mean amount was 31.38 ounces. Is this an unlikely result? Is it likely that the process is putting too much soda in the bottle? Is the sampling error of 0.18 ounce unusual? Let's take a look. So we know that the sample mean was 31.38 and the population mean is 31.20. And we also know that the standard deviation of the population is 0.4, which is known at this particular case. And then we know that the sample size is 16. So basically we can use the Z formula, which is the sample mean x bar minus mu divided by sigma divided by square root of n. So it's 31.38 minus 31.20 divided by 0.4 divided by the square root of 16. So basically we can get 1.8. So basically we can conclude that it is unlikely that there is a less than a 4% chance the process is putting too much soda in the bottles. Where do we get the 4% chance? So basically what we can do is that for Z equals to 1.80, we can take a look at the Z table. And from the Z table, we know that the probability from 0, which is the mean, to 1.80 is 0.47 for 1. And so the difference is 0.359, or we can round it up to just about 4%. Okay, so this is the end of our discussion for chapter 8, and we'll discuss the next chapter on estimation, which is on chapter 9. Thank you, everyone.